Hello friends, let's have a look at the last minute revision for paper 3. 2 years ago, I made a video for the preparing for AA students, going over the general topics on paper 1 and paper 2. But for today, I prepared something for the paper 3 to prepare for your May exam. So let's get to it. So the contents will be the following. Yes, first of all, I'd like to mention about that it's important for us to use a calculator to get some clue of the unseen topics. And also I'd like to talk about the 2 key techniques for paper 3. This goes for, I think not only just paper 3, but any competitive math that you are doing for your preparation is called the learning phase and proving phase. So we should be able to use a technique that is given in the context of a problem and then use it, apply it accordingly for new types of questions. Okay, then yes, I'd like to talk about where we can get those paper 3 problems, especially where does it associate, and then we can then elaborate some of the examples that we can practice for the upcoming exam with a particular interested in something called a Basel problem. Okay, without further ado, let's get started. Sure, so first of all is what I want to show you is something that to remind you that in paper 3, even for the AA students, you're allowed to use your calculator. So when you are using the calculator, you want to gain some insight to tackle the problem. Let me quickly show you one example from 2016. In the 2016, yes, it was not in the distinction between the AA or AI, and Ocean had a very different approach. But this particular problem has the spirit of paper 3. So let me quickly talk about what I mean by that. So here, you absolutely don't need to know what it means by alternating series per se, but let's say that we were given expression of this series, okay? And then this series is oriented by the following sequence where it's given by the following expression. My sequence here is to find the definite integral of a function sine t over t from n pi to n plus 1 pi. So we are actually evaluating an integral on the consecutive integer pi, okay? And here we have to explain why this series is alternating. And to me, actually, to prove that this is alternating without the use of calculator or without having the previous understanding of this graph is actually very challenging. Okay, this is college level mathematics. However, what you can do is to understand the context of the problem. You see, what we're trying to do is to prove that this sequence is alternating. Okay, and then this sequence now is based on the integral. And if you think about the integral of the expression, what can you think of? Very good. We can think of actually finding an area. And to find the area, what we are supposed to do is always to graph the function and see the behavior of the function based on the graph, and then find the area accordingly. Because just doing the integral doesn't give you the area, right? Okay. So let's quickly see the graph of it, right? So on the xy plane, let me quickly show you the sine x over x. Even though it is a very popular function, it's not in the syllabus. You see, however, you get to learn this as in the early chapter of differentiation of the sinusoidal function, because you use this function, especially the limit as x approaches to 0. But then the sequence of this integral was a sequence of the series was something like the un being n pi to n plus 1 pi. Of a sine pi of a sine x over x, wasn't it? Okay, so that we already established that is to find the actual area between the consecutive integer pi of the graph. And if I haven't sketched this function on my calculator, it would have been very difficult for me to visualize this one on my own, right? Although it is possible in terms of a function transformation, right? We are dividing by the x, and then the oscillation is going to change. However, finding the limit would have been quite complicated. And however, with the help of calculator, I gained the insight. All right, so if I try to go for the 0 to pi, for example, when n is equal to 0, my area here is going to be above the x-axis, which is going to be positive. But if you look at the next integer pi, such as a pi to 2 pi, you realize my area is going to be negative. And then the pattern goes on and on. It was a positive, negative area of the integral. And from then you can say that, yes, it is an alternating. You see? And for paper 3, if you see some unseen problems, and if you could sort of imagine the necessity of use of a calculator, that's a great start, right? And then to actually gain the knowledge of that I have to sketch this function based on the fact that you are already able to associate the concept of area with the expression of the integral given in the sequence, you see? So using calculator doesn't give you the answer necessarily, but it gives you a clue if you have the a right understanding, a right context of the problem. That's the first thing that you should remember from the paper 3. If you are able to gain some insight from the graph or use some values, you should definitely use it. I believe in the previous exam in maybe 2023, you had to deal with something like the gamma function, right? It was the integral from 0 to infinity of e to the power of negative x times x to the power of n, right? And for that, you had to sort of see what happens when n is equal to 1 or 2, and then you saw that it becomes 1, 2, and 6, and 24 etc., which then sort of gives you the pattern of a factorial, you see. And then therefore gaining insight from the calculator is important, and it certainly helps, right? That's the first thing that I want to mention for the paper 3. Now let's quickly show you the visual of the area. So if this was a sine x of x, and then what we had to do was to find the area of using the integral. And if I quickly show you the behavior of the area, yes, it's going to be plus minus, showing that the sequence is actually going to be alternating. Right? That is great. And then, but however, algebraically, of course, this is the AA, right? Even though we are allowed to use calculator, maybe you would most likely do that for the graphing or quickly computing some value. But essentially, the essence of paper 3 relies on your actual work by hands, right? And then the most important thing here about the paper 3 to me is about the learning phase. Most questions will be unseen, likely. However, it's going to have a historical significance in mathematics, as well as it's going to contain a lot of algebraic skills that you already have polished during your paper 1 and paper 2 practice, right? Thoroughly from topic 1 to 5. Okay, so let's have a look at one exam question from May 2011, right? So November 2011. So let's gain some of the question from the learning phase of paper 1 or 2, and then let's try to elaborate to exam question for the paper 3 that could be a bit more advanced. However, which is going to rely on the skills that you already have acquired from the previous section. Okay, so this question is going to give you insight for the learning phase. So let's see what I mean by that. So yeah, so this problem is beautiful because not only is it algebraically challenging, but also it talks about something called the Fourier series. So if you're interested in about Fourier series, about a relation between the complex number and Fourier series, I strongly recommend going over this practice and try to analyze the concept out of it. So yes, the modulus is a definition of a complex number, so we know therefore it's going to be, what is it? Modulus of cis theta is equivalent, right? Because Euler form and cis form is the same thing, and then so that's going to be modulus of the cosine square plus sine square, which becomes simply just 1. So I'm very happy. Okay, no problem. Let's have a look at the next page. So here I was given this geometric series where this is an infinite series, and hopefully this is an infinite geometric series with a common ratio with the signs between -1 and 1. And yes, we had to prove that the size of the common ratio here is going to be actually 1/3, and that's absolutely not a problem because we saw the common ratio is 1/3 e to the power of I theta, and if you actually put the absolute value on it, you simply just get 1/3 because you already proved that the modulus of the Euler form was simply just 1 using the Pythagorean identity. That's great. And let's have a look at the third one here. So now we've got an expression for the infinite series, right? So here, for the infinite series, there are two things you got to do. So you need to know the formula, but also you need to know simplification because you never want to put the complex number in the bottom, right? So what we can remind ourselves is that, yes, we're going to start with 1/1 minus 1/3 e to the power of I theta. But first of all, yes, we're going to get rid of the complex number in the bottom, but also I want you to make sure that you don't want to deal with fraction too much, so you can just multiply by 3 and top and bottom by on the fraction, so they simplify and start from here. Okay, let's see how we can simplify the expression of the infinite series in the next slide. And also, we're going to use that to find expression of a series of a sign. And you're going to see this type of a spirit of a problem with the complex number problem because you somehow deal with a huge amount of algebra with the complex number, either cis or Euler form, and somehow the question untangle with the emphasis on either the sine or cosine form. And here, every time you're somehow jumping from the complex number to either sine or cosine, it's really just about imaginary part or real part. In this case, we're dealing with sum of a sine. Of course, it's going to be something to do with the imaginary part. So we're going to find the, the infinite sum here, and then elaborate and jump into and try to take out only the imaginary part and find the sum. Let's have a look. So sure, we started with the infinite series form here, right? And then that was the first term and the common ratio, no problem. And then what we can do is to multiply by the conjugate, right? Because we never really want to have a complex number in the bottom. right? So, and then please make sure, you got to be careful. This is a very common mistake. The conjugate of a complex number doesn't necessarily put the negative coefficient on the complex number. Is the following. So when we have a z plus omega, often people make the mistake of this being z minus omega. But that fashion of putting the negative is only for the Cartesian form, you see. So you got to be extra careful, my friend. So in fact, if you just put the conjugate on the sum of the complex number, in fact, for the difference as well, the operation remains the same, but we just apply the conjugate on the complex number distributively. Okay, so that's what we do. So and therefore, if you look at the, for example, 1 minus e to the power of I theta, let's say, as an example, if I put a conjugate on it, you shouldn't change the coefficient of the complex number only for the argument, because that's what we do for the conjugate on either cis or the Euler form. Okay, so this is going to be then 1 minus e to the power of negative I theta by the definition of conjugate. Do not just put the negative there. That's a very, very common mistake. Okay. All right, so then we try to simplify here, and as you can see, we got the sum and sum of complex and conjugate. As you know, it's a real part, isn't it? So this is going to be twice of the real part, right? It's going to be therefore, what's the real part of the Euler form? You're absolutely right. It's a cosine, isn't it? So then we have the twice of the real part, which is 2 cosine theta multiplied by 1/3. It's going to be 2 over 3 for the coefficient, no problem. Okay, that's lovely. That's lovely. So that is a complex form. And of course, in the numerator, what we can do is group by the real and imaginary part. So the real part here, my friend, is going to be 1 minus 1 over 3 cosine theta. And then the imaginary part there is going to be I times sine theta. Sorry, over 3. That's my imaginary part. And as you can see, as you have seen before, what we wanted to have is to talk about the expression for the sum of the sines, for which then you would use the imaginary part, isn't it? So let's have a look at the next example. So now we take only the imaginary part of the geometric series from the Euler form. Beforehand, we had the 1 plus 1 over 3 e to the power of I theta plus 1 over 9 e to the power of I theta square. Goes on and on and on, but in order to induce only the sign, we're going to take the imaginary part of the series, which then came out as just the 1 over 3. Forget about the 1, that's just a real number, right? It wouldn't be the imaginary part, is it? Because it's not in the multiple of I, okay? That's correct. And then from the simplified form of the geometric series, we can only take out the imaginary part because we are only comparing the series of the imaginary part and then the one imaginary part from the one that we actually simplify using the geometric series formula. Okay, so that's correct. So now this must be equivalent because whatever the expansion of the complex number, if it's the same, the real and imaginary part has to be the same due to the complex equality. Okay, that's great. And then we can then obviously simplify the top and bottom. Okay, and then we got this following example by multiplying the 3 on both sides and then simplifying the form will give you the imaginary part as the following. Okay, so now I just went over a paper 1 problem with the complex number that would have been using for the learning phase, you see. And what you do after that is to work with the proving phase, right? So proving phase associated with some of the skills that you already have learned from the previous part, and then use it for the next part, which will not entirely rely on your learning phase, but it would definitely use a significant parts of it. Okay, so that's very important to realize. All right. All right, so let me quickly show you what it means by the proving phase. So what we want to do is to apply the understanding that we have gained from the previous part. Meaning, imagine that I was given this series, okay? Imagine that I was given this series. And for me, actually to derive the general formula of this series is very complicated, okay? Because it's actually n many cosine term, and for the sum of the cosine term, we might have learned the sum to product, but then we got n many term. I don't want to use the vector formula n many times. That would be very, very complicated, especially with the simplifying for the angle, okay? But what you can do, after having learned the learning phase from the complex number, realizing that the sum of sine can be calculated by the geometry, by the sum of the exponential, and then use the imaginary part, I can probably do the same thing. Now I'm doing the sum of the cosine, where then you can use the sum of the Euler form and the complex number, and then deal with the real part, right? That's what I want to do. So let's see if you can actually jump from there, right? So from the learning phase, I realized for the finding the series of a cosine, even though the question didn't tell me anything, I am able to figure out the clue that I would like to use actually the complex stuff first. Okay, that's a very important realization. Okay, so let's take a look. So what have we learned from the previous question? That's the essence, my friend, of the, what is it, the learning phase to the proving phase. So now I'm going to deal with what? Are you going to deal with the imaginary part or the real part? Yes, I like to actually deal with the real part. So now I know that's going to be the real part of the following, what is it, the complex series here. And yes, there are many types of a series, but essentially we learn arithmetic or geometric series, isn't it? And for me, of course, in this case, I hope that, it's going to be one of them. And of course, it's very easy to see that it's going to have the common ratio of, what is it? Common ratio is going to be e to the power of I 2 beta, because as you can see, to raise the argument, you got to multiply by some number, and then it goes by the common ratio of e to the power of 2 beta. Okay, I. All right, so that's correct. So my common ratio here is going to be e to the power of I2. So that's great. First of all, it's just simplified by the common factor of e to the power of I alpha, and here then therefore we can use the nth term of the geometric series, right? So to quickly remind you, a1 1 minus r to the power of n over r1 minus r is going to be the formula that I would use for this series. So let's quickly use it. So if I do that here, well, order doesn't matter, right? So I wrote 1 minus r to the power of n. Well, you can write so certainly r to the power of n minus 1, which we just did, right? And here there are two rabbit holes you can go. Okay, so here's the thing. Okay, I got it. We got the we got the clue from the question that I like to deal with the real part. I got it, right? So I use the geometric series. However, the learning phase doesn't give you everything. So proving phase, you still have to come up with your enticing method to simplify the answer. So for me, when I see this problem, there are three approaches you can do. And then in the slide, I'm going to show you the simplified one. But I really want you to try yourself if you can actually derive the same answer by the method that I tell you now. Okay, so first of all, yes, the common practice for us is that when we see a complex number in the bottom, we like to multiply by the conjugate. So what I like to do top and bottom, I like to multiply by the same number, which is going to be in the conjugate of what? It's going to be e to the power of negative 2 beta I minus 1 is going to be my conjugate, isn't it? You could have done that, right? To me, however, it doesn't give you the most simplified form. Okay, so that's one rabbit hole. The second rabbit hole that you could have fallen into is that, okay, so you know what? As we already have done before, when we see the product of complex number, what you often do is to add by the argument. Okay, no problem. But for a significant number of questions in the recent past, I really hope you realize that. I really hope that you realize there were many applications of a sum of complex number, which you can either prove by vector or trigonometry. I really strongly encourage you to try both. Okay, but if I could quickly show you the formula, you can do this as 2 cosine theta minus phi over 2 cis theta plus phi over 2. So that's a sum of a complex number. It appeared many times in the recent exam. Please learn this method, okay? And therefore, you know what? For example, the denominator, you can actually convert that into some of the complex number, right? That's just the cis 2 beta, right? I mean, you can keep it as the Euler form, but for me, it's working better with the cis form because it sort of mimics with the trick, doesn't it? And the minus 1 is in fact cis pi, isn't it? So you can actually use this method. You could have done this as a 2, therefore cosine difference divided by 2 is going to be 2 beta minus pi over 2. Sure, why not cis? And the sum, pi over 2. And then as you can see, what we can do here is to use the complementary angle. So that would become sine, sine beta, right? So then you could have done on the numerator as well and try to simplify and further. You can do that, right? But this is still not the most efficient here, okay? And let me quickly show you what's going to be the most efficient to tackle this problem. Therefore, for any math problem, there are many different methods. And what we try to sort of aim for during the exam is to try to find the most efficient method. However, in your practice, do not be afraid of, falling into the rabbit hole and become the Alice in Wonderland. That's absolutely welcome in math, especially if you just wrestle with one problem that you think you almost got it, but you're still missing the gist of just one tiny step of it. Don't matter. You can take as much as time you want on your practice. I think it really does practice you well. Okay, but let me quickly show you the next problem. So yes, here what I try to do is to I try to factorize a common factor of e to the power of negative I beta here. Okay, so that's great. And here on the denominator, on the numerator, I'm going to factorize both terms by e to the power of I n plus 1 beta. And then the reason we have done that is the following, because now you see on the top and bottom, what do you see? You see the difference of a complex number is conjugate, for which you already know that the difference of a complex and conjugate is the twice the imaginary part of the complex number. So I can actually immediately change this into the trig function. It's going to be, what is it, twice of the I of e to the power beta, that's his argument. And the numerator is going to be twice times the I times the sine of n plus 1 beta, for which that's going to be the argument, isn't it? So then it's a lot easier for us to simplify it, so rather quickly, right? For previously, when we did the sum of complex number, we had to use the complementary angle vector formula, blah, blah, blah. But for this one, we can simply use the sum of complex conjugate, and that's done there. Okay, so then now we are trying to get the real part of it. Now that will be considered as the modulus, isn't it? That will be considered as the modulus. So that remains the same. Have I written? So that remains the same. However, for the real part of that will be simply just a cosine, and that's done of the question. You see? So for the complex number, it's really two things. Learning phase, you're going to most likely to deal with things you already have learned. For example, in differential equation, they're going to ask you to meddle around with the homogeneous, integrating Euler's method, whatever. But it may introduce a new technique for which you don't need to know absolutely everything, but you still have to apply something new to it, like the auxiliary equations or showing that the linear combination of solutions is going to be the solution, things like that, right? Or what is there to be also think about from the previous question, like the arithmetic mean versus the geometric mean. We don't really learn the syllabus. However, it can definitely be given as a question and proved by the induction, for example. Things like that. And then the recent one also had something like the surface area, doesn't it? Even though you may not be required to prove the surface area during the test, that's just a long task, but they will ask us certainly why this formula is better than the other, and hence we can use, for example, finding the surface area of a sphere with this given formula, things like that. They will not give you the formula for free. You have to still gain some insight from the previous learning phase, which is going to most likely to be associated with things you already have learned. And for the proving phase, you might see something new, such as a surface area, things like that. And you cannot tell me that I haven't learned this, so I can't solve it, because the questions are built in a way to assist you to gain the insight from the learning phase and then use it accordingly. So that's the essence of paper 3. However, as you can see, the algebra can be challenging. You see, we're going to challenge you algebraically or mathematically, whether you can choose the most efficient way, which is the essence of mathematics and optimizing. So that's great. So now, yes, let's talk about what sort of questions can come up. But there's so many, right? So if you actually go through the paper 3 problems from 2021 up to now, it has been always something significant. Haber's formula of the sum of integer square, or cubic formula, or fundamental theorem of algebra by Gauss, or hyperbolic function, or Chebyshev polynomial. There's so many, like differential equation of a second degree, and then trying to find the general solution or prove that it is a general solution. Things like that. There's so many. There are so many questions that has been or is not seen yet. I'm sure there will be some Basel problem from time to time. There still hasn't been many topic 4 paper 3 problems, and I think there are many great questions like proving covariance or generating function to talk about the expected value, things like that. Right? There's so many. So and if you're school teacher is very keen on actually showing you those paper 3 problems. With the history, you would have already seen the problem at least once, and that's wonderful practice, okay? But most of the time, I think, to me, for the IB students, they get to see those questions a bit less because, first of all, it's international school, so the faculty of the department is very unlikely to stay for a long time. Hence, they cannot really fully accomplish of their passion to teach, you see. So it takes time, and therefore I'm trying to sort of elaborate some topics that you can have. But yeah, it's going to be based on always all those historical, significantly important mathematical ideas. Gauss, Euler, Bernoulli, Chebyshev, whatever. There has been many. So those questions already have appeared in either paper 1 to 3 throughout the history of IB mathematics. Okay, so what can come? There's so many topics: recurrence relation with the Fibonacci sequence, or finding the general solutions, quaternion with the complex and vector. And I think that would be a very wonderful question to talk about the unit quaternion and how it can use for the rotation. I think that would be very wonderful for your series. Something with the complex number. The very first example that I gave you from November 2011 is actually to associate with the Fourier series. And you should actually try to graph the function. I believe it was like sine theta over 1 minus blah blah. If you actually plug it in, you will see a very repeated periodic sort of a linear function, and you can sort of see, oh, okay, so this is an interesting way to start for my IAE. That would be a very good insight. Generating function for the probability for proving the, for example, the expected value or the variance of your binomial distribution. Error function to associate with something like the integral and normal distribution. Dirichlet's integral is also a very nice example to see Bernoulli numbers with the binomial expansion and Pascal's triangle, and how we can elaborate the pattern of the number and then use it for maybe the Maclaurin series of a tangent. There are so many examples. Pigeonhole principle, but we can learn but obviously it's impossible to go over all that. But for you to prepare for the paper 3 is not to memorize those type of historically important questions. Even if you are encountering those new type of problem, what you are supposed to do is to see whether you can gain the deductive thinking from there and apply to the new type of question. They don't ask you to prove fundamental theorem of algebra right away. They will give you some clues beforehand. What you have to do is to make the connection between the dots, okay? With your deductive thinking. That's the most important thing. That is the single most important thing in mathematics. It's the science of deduction. All right, so and for me, there are many types of inspiration for paper 3. There are many questions on the revision village or many IB task manager, whatever. Sure, but to me, okay, what goes up comes down in life. Yes. If I ask you what, something about Wuhan, arguably, there's an issue with the COVID, right? The one way or the other. But in that era, in 2019 or 20, there's something, when things went south, there are also things that actually jump up, that went north. A paper 3 collection was released from a teacher in I believe Wuhan school, and it's a beautiful document. It's a pure respect for him. It's got many exam questions that I believe would probably be enough for you to practice with the paper 3. And a lot of school unit tests also relies on this document for the paper 3. So I strongly encourage you to practice with this document. It's a beautiful set of questions. I believe it's probably inspired by many college math department interest exam questions, as well as other high school diploma exam. But for me today so I gave you 2 information, the 3 information total so far. Use of calculator to gain the insight, and then about the learning phase and proving phase. Okay, and the third one will be where you can get a bunch of questions. And I think his document, the Daniel Huang's document, Mr. Daniel Huang's document for the paper 3 is more than enough for you to really, to relish the type of paper 3. Okay, but for me, let me come up with something more interesting. I think one day you definitely have a Basel problem, and for me, I'd like to talk about this legendary problem of showing the sum of 1 to 1 over 1 and 1 over 2 squared, 1 over 3 squared, goes on and on for the infinite sum will converge to pi square over 6 as a paper 3 type of question, as taking this opportunity. And then I'll talk about the 4 types of paper 3 problems and show you where you can gain the learning phase and use it for the proving phase. Okay. So first problem I like to associate with the De Morgan's theorem from the complex number. Second one, I would like to use something called the divergent series. Okay, and then, which is also something to do with the complex number. The third one, I like to use the calculus with the Maclaurin series. And fourth one, I would like to use the reduction formula for using the integration by parts. So reduction formula is really just a fancy way of using the integration by parts in many times. Okay, all right, let's go. So for the first one, about the problem, I like to use complex number and DMT. And let me give you a learning phase from, again, the previous exam question, let's say in November 2014. Okay, so here what you had to do was to simplify this 1 plus tangent I tangent 1 minus negative 1 minus I tangent theta to the power of n into this following form. Okay, obviously what we can do is every time you see power my friend, you want to use a DMT, and for that you got to put into the cis form. And right now 1 plus I tangent theta is not in the cis form. Well, that's okay, because what we can do here is put it into the common denominator cosine theta, and then and put the real part and then the imaginary part, isn't it? Right? So that is great. Then I can put what is it to the power of n, then we can use the DMT on the complex number right away. Okay, let me quickly show you on the next slide. So this is what we had, right? And then from here, what I try to do is put it into the common denominator. Okay, that's great. And realize that, the 1 minus sine tangent theta, because the tangent is odd function, we can send it to the argument at being negative, right? Because of odd function property. And now we can directly use the DMT there because it's in the cis form, right? The real part is in the cosine, the imaginary part is in sine, so I put that in the cis form. But as you can see, this is going to be sum of the, complex and conjugate, so imaginary part cancels out, and the cosine is an even function, so even though I have a negative argument, boom, it's going to be simply just positive, so it's going to be just twice of the cosine, isn't it? So that, my friend, is going to be the proof of it. Okay, easy peasy lemon squeezy. So now you show that even if you have a tangent in your real or complex part, you can still derive the DMT using the common denominator, and I like to do that for the next sort of a proving phase question. Okay, let's have a look. So now I like to simplify the following example. Now I'm given the cotangent. Easy peasy, lemon squeezy, not a problem, right? Because I again have gained this understanding, from the learning phase to put it into the common denominator and put a cis form, and maybe to associate with the sum of the complex conjugate or difference. Let's see what's going to happen in this case. I smell that it's going to be the difference of the complex and conjugate, so it's going to be twice of 2 times I times the imaginary part, which then 2i can be simplified further by dividing by on the denominator. That's lovely. That is great. So let's see what we can do. So now we got this one, right? So I would just work with on the first part because the second part is just obvious to work with. But for this one, then I put it into the common denominator of a sine. Then I have a cosine and I sine here. Then no problem. Then I can put the DMT there. That's going to be cis 2n plus 1 theta, right? So that's great. So if you simplify that, So that's what we have on the first term. And then, for the second term, you're going to have the same thing, but it's going to be, the conjugate, right? And here, if you, then subtract, only the real part will cancel out. Again, the imaginary part, it's a sin, it's sin. The imaginary part will get double, so that you're going to have that identity here. Okie dokie. So that's great, right? Easy peasy, lemon squeezy. We got this idea from the learning phase. But here's the thing, for the proving phase, the question could ask you, okay, now simplify this, expand this in a different matter, right? In a complex number, you remember, there are many questions to compare between the cis and binomial expansion, right? For example, in November 2023, you had to find the angular form of a multiple of a 5 for the sine, comparing the cis theta to the power 5 with the DMT, which is going to be cis 5 theta, and then the binomial expansion, and only associate with the imaginary part, right? And then we can do the same thing here. Okay, so now we use the DMT to simplify, but I like to simplify the left-hand side using what, my friend? Yes, by using the binomial expansion. So let's have a look at that learning phase from the binomial expansion with the DMT into this particular example as a proving phase. So let's go. Okay, now I'm going to associate this as a binomial expansion, my friend. So if I try to expand this binomially, but you know what? Yes, it's very tedious to use cotangent all the time, isn't it? So for me, I like to associate with cotangent as a substitution for t. Now I got 2 terms binomial, no problem. I can put it into the sigma form, no problem, like this. All right, so that's great. That's great so far. Sorry, I think it's supposed to be 2n plus 1 minus k, okay? So let me quickly erase that. It's supposed to be 2n plus 1 minus k, okay? All right, so now I got I wrote it here, well, right? And then I got the second one here. However, I got the negative term in the second term here, and therefore, it's going to be alternating series. It's going to be alternating, my friend. That means it's going to be odd for, it's going to be negative for the odd term, okay? But now I'm going to see the difference of it, isn't it? So who's going to cancel out of the same term, but then it's alternating? Yes, you're right. Only the odd terms were alternating, but if you subtract, it becomes a double negative, hence it gets double. But for the even term, when they have the same sign, if you actually find the difference, that's going to get nullified, all right? So now what we're going to be left with is just the odd term here of the expansion, right? So let me just do the algebra here, and then if you expand, what we also expect is that I'm going to be just left alone with only the odd terms. Oh, sure, odd power here, my bad. I'm going to left with just odd power like that. Sorry, odd coefficient, right? This one being k being 1, k being 3, etc., etc. And then let me quickly show you why we have a t to the power of 2n. Let's quickly go back to the previous slide. So what we want to do here is actually we had the power of a 2n plus 1, you see? We have a 2n plus 1. So if you put k equal to 0 here, my friend, with the even term, we have, plus 1. So if you put k equal to 1, k equal to 0, I start with 2n plus 1, you see? So for the 2n plus 1 chooses 0, that's going to associate with t to the power of, 2n plus 1. But if I go with 2n plus 1 choose 1, I'm going to associate with t to the power of, now I subtract by, it was a 2n plus 1 minus k. So if I put k equal to 1, that's going to cancel out. It's going to associate with 2n, you see? So the odd term on my binomial coefficient is going to associate with the even power because of the 2n plus 1 here. Okay? All right, so that's better. So yes, now what we had there, I really want you to try yourself as well, is that this is actually true. That whenever we have odd, it's gonna survive. And however, it doesn't give you the odd power because of the power of the 2n plus 1. It got raised by one more term. So it's actually going to be 2n minus 2, etc., etc. So that was a difference, my friend. That was the difference. Okay? So that's great. So now then we got two expressions here, isn't it? So first, we had the expression of this one using the DMT, and we got the second expression using the, binomial expansion. Right? So the one that we have used with the binomial expansion came out as such. So that's great. So then what you can do is you can compare the one with the DMT, and you can compare with the one from the binomial expansion. Okay? So let's do that. All right? So let's try to do this polynomial expression of that using this trigonometric function. And as you can see, as you remember, if you want to somewhat associate with the polynomial, what is the best value to find? You're right, I want to find the zeros of this polynomial, right? That's usually our job to do with the polynomials, right? We want to find the solution of it, like the quadratic, at most 2 solutions, cubic, at least 1 real solution, etc., etc. And for me, having this expression of a sign really helps me to find the zeros of it, right? Because if we have sine 2n plus 1 theta being 0, then you can easily find the solutions of this value to being 0. So if I put that x value in that case, it would simply be 0. No problem. And yes, I hope you realize I changed this into degree n polynomial by making another substitution. I let the t to the power of square as an x, right? Because then I can put it into the degree n polynomial. So then now we know by the fundamental theorem of algebra, we are only associating with the n many solutions, at most in real number, or exactly n many solutions in complex, right? So then yes, let's try to use this periodic function here for this sine 2n plus 1 theta to be 0. I want to remind you that the sign is a 0 whenever we have an integer pi. Okay? So now what we can do is this 2n plus 1 theta, I will let that to be the integer pi. Right? So from this polynomial expansion here, we know the sign has to be 0 like that. And to do so, what we're going to do here is a 2n plus 1 theta as an integer pi. Okay, so that is a great. So that is my integer pi here as a solution. And depending on the size of r, we can choose n many solutions, such as r being 1, 2, all the way up to n. Then we have exactly, n many solutions in this case. Okay, that's great. And how can I use it for the x? Well, x was, what was it? It was a t squared, wasn't it? And for t, we use the substitution for the cotangent, right? So it's going to be cotangent squared theta. And luckily, we already found the expression of a theta, right? Thanks to this x will be 0 if we have this argument r going from 1 to n, exactly n many, which is satisfying for the fundamental theorem of algebra. That is quite marvelous. That is quite marvelous. So now we know this is going to be my general solutions, where r being starting from 1 to n, right? Non-zero solution. Easy peasy, lemon squeezy. Okay, so what do you remember from the polynomial when you know all the roots? Well, what you can do is when you know all the roots, there are two things to remember from the learning phase of working with the polynomial, which would have been probably given in the question. Yes, you remember something to do with the sum and product of roots. You know the recent exam question in the polynomial had a lot of sum and product of roots. So, and of course, you can do something with the Vieta's formula in the paper 3, which happened, I think, at least once for the past years. So make sure you are able to conceptualize with the polynomial and sum and product of roots. And so for here, I already know all the roots of this one. And I also know the coefficient of the first two coefficients of the leading terms, right? Then I can definitely talk about the sum and product of roots, isn't it? So now I got the roots here, and then the sum of that is going to be the, what is it? The negative of the second leading term and then the first leading term here, their coefficient. Like that, using the Vieta's formula. No problem. So then I can associate with my coefficient given already here. If you use a combination to simplify, I'm given that. Okay? The sum of all the cotangent now became this. That's quite great. That's quite marvelous. And we know all the roots already are being from 1 to n to associate this series of a cotangent becoming as the following expression of a rational number. Okay, that's great because cotangent is a trigonometric function. It's something to do with the transcendental numbers usually, and then that actually converges to something with the rational number. That is great. That is great. Okay, so now we cannot write this series all the time, and then I simplified as a use of the expression of a cotangent. So that's what we have. Okay, but my learning phase doesn't stop it from my proving phase doesn't stop it there. Then I go to the next part of the question, which may not be associating with the previous part, but as a new start of the learning phase. Let me quickly show you. So I hope you realize this is essential, one of the most crucial inequality that you learn in calculus study, because we often use this for the proof of the limit of the the limit of the essential limit of the trigonometry, and then use it for the fundamental limit of trigonometry, and then the principle, the first principle for the sine. And please, learn this, and then we have it also in the video that I believe you can associate with this type of a sort of triangle, and then compare with the triangle sector, and then the tangent right angle triangle, and be able to derive this inequality. Okay, let's suppose we have that. And then what I want to ask you is whether you can elaborate this inequality into the following. Okay, how you can elaborate that inequality to that one? I want you to pause the video and think about it. Okay. Sure, I mean, it's got something with the square, right? And it doesn't hurt us to maybe put it into the perfect square. So if I put a perfect square on both of them, what do we have? I got the secant square, sine square, tangent square. Okay, so that's great. However, it is nothing to associate with my reciprocal, so maybe I will do the reciprocal. Okay, so why not? So let's reciprocate both sides. However, remember, it's inequality for the value between 0 and pi over 2 for the angle, so it's always a positive. Right? Sine and tangent are both positive in the domain. So if, for example, reciprocate the 2 and 3, the inequality changes for the positive number, and I can do the same thing for this case. So now, the upper bound being the tangent square, if you reciprocate that, it's going to be the cotangent square, and then that's going to be actually becoming the lower bound based on this logic here. Okay, then the sine, reciprocal sine, is going to be cosecant square, so that's what we have here. So I already have my lower bound. That is great. And then what you can do is that, yes, using the Pythagorean identity, cosecant square will be the sum of 1 plus cotangent square. So no problem, okay? So this will be the learning phase. Where can we use it? Well, previously what we have done was to compare the polynomial and the trigonometric function using the binomial expansion and the DMT. And then we found n many roots of that polynomial using the trigonometric function. That is great. And we also found out the sum of roots being the ratio of the, the negative an minus 1 over an using the Vieta's formula. So we have it, right? We have a sum of cotangent square, you see? So if I put a sigma on it, maybe I can associate this inequality with something greater, because I already know the theta thanks to the trig identity that we derived from the DMT of the numerator. Okay, so that is the logic behind to transit from the learning phase to proving phase. All right? So let's have a look at this one. So now what I will do is put sigma on it. Why? Because I really want to associate with this value, because I already know this one, because it's from the sum of the roots of the polynomial. Right? That's great. We already had a theta. It was something like something over r over 2n plus 1 pi, something like that, right? I can do the same thing here. Why not? So from the Vieta's formula, we already know the sum of the cotangent square with this particular theta was given as such. So let's try to apply this on our inequality right away, right? And sigma, so the theta here, if I put that in here, it becomes reciprocal. And then if I take out everything but the index r, we'll have that coefficient here. No problem, okay? That is great. So then let's, the inequality that we already had before, where this is going to contain both of them. And then that one is from the sum of roots of sum of the polynomial. This, we already found the expression of the general form. And that one, by using the linearity of a sigma, it's going to be sigma 1 plus sigma cotangent square. We already have the expression for that one. And then sum of constant value is just the one, edit one n many times. So that's going to be simply n, isn't it? So now I also have the expression for the right-hand side as well, right? So then if I use the expression there, that expression from the sum of the roots here, and then that is the sum of 1 here, just being n, and now we got this expression here. And what I like to do is just isolate this sigma here. That means I'm going to multiply by the pi square over 2n plus 1 square on all sides of inequality, which is not going to change the direction of inequality because it's a positive number. It's a perfect square. So if I do that, we have this following inequality. And what do you think we're going to attempt to do for the Basel problem, which is the infinite sum of this? Now I'm going to take the n to infinity. And now we got the inequality here. Very likely that it's going to use the squeeze theorem, right? So let's have a look at the squeeze theorem of this. If I send n to infinity, I'm probably interested in the coefficient of the n squared because that's the leading term. So here the n squared it's got the coefficient of a 2. And here I got the coefficient of, what is it, 4n squared. Okay, that's great. So if I send n to infinity, this 2 is going to cancel out and have a 2, so denominator is 6. So the limit of the limit of the lower inequality, lower bound is going to be pi squared over 6. Okay, the typical limit. So if you look at the right-hand side also, the leading term on the numerator here is the quadratic, or as well as the denominator being quadratic. So for me, it's going to be just associating the limit with what is it? So that's going to be 2n squared plus whatever over 3 times, what is it? This is going to have a 4n squared plus whatever, okay? But obviously we're going to divide by n squared here and then try to send n to infinity. Anything but the quadratic term will just vanish to 0 because it will have some sort of n in the denominator. And if you send n to infinity, denominator being infinity will give you the 0. So here now I have, what is it? 2 cancels out, so I will end up having here also pi squared over 6. So by the squeeze theorem, you can prove that the lower bound, upper bound give you the pi squared over 6. Hence, whatever the sum that we have in between must be squeezed to the limit of pi squared over 6, which is the proof of the Basel problem using the, what is it, complex number. But it came from, the inspiration came from what, my friend? Yes, November 2014. I hope you realize that all the exam questions that you do and then you find it challenging, it's got a reason because they are based on the historical aspect of the mathematics, right? But you don't need to know them. Of course, if you know it, that's better because it will give you an interest to learn them, right? But those algebraic challenging problems, if you see them once in a while in the exam, please exam practice. You can use it, please. You can use it for your internal assessment idea, and that would be a great paper, okay? But that is the first approach of the Basel problem. Let's now have a look at the second approach for the Basel problem using, again, the complex number, but now I'm going to use something called the divergence series. Let's take a look. All right, let's have a look at the second approach, the Basel problem number 2 using the divergence series. What does that mean? Okay, let's take a look. So first of all, I want to give you this binomial expansion, right? I want to give you this binomial expansion with the negative power, right? And then we can sort of use this, you can expand this binomially, or you can use geometric series, no problem, right? My common ratio here is got the x here, 1. And then you know what? Let me quickly sub it in with the x equal to e to the power by theta, okay? So then, this series then will become the following, okay? No problem. And then I want you to realize that what we see here, it's a complex number in the denominator, so we don't like it. So what was a multiply? What do we multiply on the bottom? Right, we will multiply by the conjugate, isn't it? So if you multiply by the conjugate, it comes like the following. Only the imaginary part will be the negative. And if you simplify the denominator and then a numerator, you get the following. Okay. So then that's great. So it becomes what is it? It becomes as such. But as you can see, I can use a Pythagorean identity. That will be simply just 1, no problem. Okay. And then, so, no problem. So we got this following series of the sum, right? And then we always, for the complex number, make sure you are willing to separate by the real and imaginary part, where I can now get rid of this as a common factor, no problem, right? So it becomes as the following. You got the half and the cotangent. Oh, hold on a sec. I think we have seen it from the previous part, isn't it? Yes, there's a significance of the binomial expansion with the 1 and cotangent. You can actually elaborate and maybe talk about something called the Bernoulli number. Okay, but anyway, so we'll move on. All right, so we got this following. Oh, sorry, it's a theta here. We got this following expression, right? Equivalence of the one from the geometric series, and then we simplify using the complex identity such as a conjugate, and we got it. And now what I'd like to do is maybe just associate with just the real part, where we know the real part on the right hand side will be the half, and the left hand side, the real part of the order for example, will just come out of the cosine. We just have to use a different argument, right? So Let's use that. I got this, you see? And then I can associate, I can rearrange maybe the half on the left-hand side. I got the positive half there too. No problem. So this is what I have, okay? So this is the expression, right? That's great. And then what I want you to do is also, now we are still doing learning phase, let's say, right? The whole point, whole essence of this going over the Basel problem is, I don't know if this is ever going to be asked you, but I really want you to gain the deductive thinking. And here, the deductive thinking is that I want to put my angle here as x plus pi. Okay, so I plug in, no problem. And then what you see here is that you can use now the identity with the, the reference angle, right? Realize if I do, pi, and then go pi further, that I'm located in the third quadrant, so cosine is going to be negative, isn't it? So all the rest will become just negative there by using the reference angle. Please make sure that you're aware of it, okay? Sorry, for the odd pi, my bad, odd pi, because if it's a 2 pi, that's just a period, and then I went by 2x again, so that's going to be positive. So by plugging this x plus pi, the odd pi will be negative, and even pi will be positive. It made everything alternating, so that is great. That's good, okay? So if I do the rearrangement there, I get this to be half. Well, hold on a sec. I saw the similar thing, right? Previously, we saw this was the one that we just got it from the, the alternating term, and what you can do is to integrate both sides. Let's try to integrate both sides. I'm still giving you the learning phase. All this integral, you're given for free. You are not asked to come up with this integral. The question gave you. Okay, no problem. Let's do that. Well, then the integral of the cosine will be simply just a sine, and every time we have this linear substitution, by using the substitution, we gotta come up with the reciprocal, right? So that will be, sine x. That will be 1 over half sine 2x. That's 1/3 sine 3x. That's a quarter sine 4x, right? So exactly. Then we plug the 0 in pi. Well, the sine evaluation at 0, it's gonna be all 0, so I'm only interested in y. So I got an expression. I got an expression of a nice alternating series of a sine. Okay, that is great. Then on the right-hand side, if you integrate that, it becomes a quadratic, doesn't it? Oh, sorry. It's supposed to be 1 here, right? Because I'm integrating the half with respect to y. It's a constant. Integrating that will give you the linear. Evaluated from 0 to 1 will be just y there. No problem. Okay, no problem. It's so easy peasy, lemon squeezy. And I will give you another learning phase, my friend. So here, let me give you the learning phase of, again, doing the integral now from 0 to z. Now I want to go back to the cosine. Okay, by integrating twice. Okay, no problem. But here, however, I got to be careful though, because now if you integrate with 0, sine will become cosine, and evaluate the cosine at 0 will give you 1, right? So it's going to be cosine, so it's going to be given as a fun. Well, the integral of a sine is negative cosine, evaluated from 0 to z will be alternating, right? So it would be the opposite. So now instead of a cosine z minus 1, I got the 1 minus cosine z. I hope you see that, right? Just very, very elementary integral. And now I can do the same thing, make sure if I have a linear substitution, the reciprocal is going to come out. So I got that, right? I got this. Okay, so no problem. So alternating will remain the same. Okay, no problem. But so what's annoying still is that I still have this massive sum of the constant part here. Okay, and let me quickly show you how we can get rid of those constant parts or make it simplified using the substitution or putting into the factorization. So here now I'm gonna let the z as a pi. Okay, and I want you to realize cosine odd pi will be, always -1, isn't it? So it gets double, you see? 1 minus -1 will get double. Where the cosine 2 pi, as you remember, is 1. So it's gonna get actually canceled out. It's gonna be 1 minus 1, 1 minus 1 here. Everything becomes a 0. So only the first and third, the odd terms will get double. So it's gonna be 2 and then twice of the 3 factorial, twice of the 3 squared, and then twice of the 5 squared, on and on and on. Right? So the expression now here, if you evaluate for the cosine and use it for the supplementary angle, we got the following odd square in the denominator, just like the Basel problem. And on the right-hand side, we already integrated the linear term into the quadratic term, but now we let the z as a pi. I got the pi square over 4. Okay? So now if you divide it by 2, what do you get? Now I got the sum of odd square in the denominator, which is very, very similar to the Basel problem. Now I give you the proving phase. My friend. Okay, so I got this beautiful sum of only the odd. How would you come up with the Basel problem, which is a consecutive integer square in the denominator, right? Right now, I want to derive the zeta function of 2, which is the Basel problem. So it's a 1 over 1 square, 1 over 2 square, 1 over 3 squared goes on and on and on, right? So now it's a consecutive integer, but I got only odd. Very good. That means I need even terms, right? So let's think about the even terms. That's the proving phase, you see. Now you have derived this odd series using the learning phase, but it didn't give you the entire thing for the Basel problem. But now you're missing with the even term, and then we would like to associate how we can go with the even term. So that's the Basel series, Basel problem with the consecutive integer. What are we missing? Yeah, we're missing with the even term only. Okay, but let me quickly see what we can do. So at first, what I try to do here is just to factorize by the 2 factorial. Sorry, I just multiplied, not factorize, my bad. I multiplied by 1 over 2 square. Okay, so I did that. So let's see what happens then. So then it's gonna be, what is it? 2 times 4 times 6 times 8. You see? It became all even because if you group by the square, that's 2 times 2. If you group by the square, that's 2 times 3, which becomes 6. If I group by the 2 times 2, it's going to be a square. It's going to be 2 times 4, which becomes 8. So now I have an even term, 2, 4, 6, 8, etc., etc. That's great, right? And what are we going to do? Now we had the odd term from the learning phase. From the proving phase, we got it from the even term expression. What we can do is simply we just add them. That's going to be then odd, even, odd, even, odd, even, having the, what is it, Basel series, Basel problem. So that is a great. So now if you add these two, I'm going to quickly have the Basel sum here. Then I can make this as a subject by making a rearrangement and simplify. Let's see. So we got this and multiply by, what is it, 4 over 3 on left and right. So that hence becoming the Basel sum as we expected. Okay. So here, what was important for you to do with this learning phase and proving phase is that learning phase we gained all the insight from this some interesting integral that we didn't know it. We didn't open up with the integral. But for the proving phase, we were lacking with the even term, so we add the extra even term. However, this question goes even deeper than that. You know, so far what we had done is actually nonsense. It is nonsense, my friend. Because if you actually return to the initial series, you know, it was given as the following, you see? And then I claim that this is convergent and hence use the geometric series. However, think about it, yes. As we have defined our binomial expansion, which was 1 plus x squared plus whatever, was a 1 over 1 minus x. And please remember, you had the condition of a convergence. The geometric series is not free. Your common ratio, in this case, x, its absolute value has to be within less than 1, right? And here I claim my geometric series with the common ratio is e to the power by theta. And then, as you know, if you put a magnitude on it, right? Well, that means the modulus of a complex number. Here, the coefficient is simply just a 1, which then cannot be used for the geometric series. Oh, wow. But here's the thing. We got into the result that we wanted. That's precisely the proof that we wanted to do. We got the same result, right? And for this one, is, you know, how, so first of all, is it really therefore wrong? And second thing is, if I have a statement, right, I got to the true. I had true here, okay? But it looks like the information that I used was a false, okay? My question is, as the statement, would that be true, right? So as you can see, you know, for paper 3 problem, even if you landed on the final destination, they will still give you the, what is it, some topics to think. In this case, I think there are two ways to think. First of all, the interval of convergence, and hence whether this was allowed or not. And second thing about the proof, right? Of this statement of truth table, I got to the conclusion of the truth, but my hypothesis was wrong. But can I still call this proof to be correct? Statement to be correct is another discussion, right? So I really want to leave it to you as an exercise. Very good. So okay, let's have a look at the third approach of the Basel problem, which I'm going to use a Maclaurin series. Okay, so and very often in the exam, you know, either paper 1 or paper 3, paper 2, you get to see this interesting function behavior of a sine x over x, and here it has appeared many times. Okay, all right. So our discussion of a sine x over x, you know, the roots here is going to be what is it? Consecutive integer pi, the integer pi, where it cannot be 0 because we saw the limit, the fundamental limit of trigonometry suggests that the limit here is going to be what? You're right, it's going to be 1, isn't it? So we saw the actual graph of it in the very first problem for the, you know, importance of use of the, what is it, the technology, right? And it was oscillation, however, its amplitude is going to get smaller and smaller and go to 0, right? It's an even function. So then, you know, it's not difficult to find the roots here because they are just integer pi, right? So now we got the integer pi. But here's the thing, when you see the integer pi, so when you see the roots, the very natural thing for us to consider is maybe the polynomial expression, because if you have the roots, you can find a linear factor, and if you multiply all those linear factors, that's going to be the same representation of the function. No problem, right? So let's try to use a factor theorem. So what I claim here, my friend, is the sine x over x will be factorized as the following, okay? Because that's precisely his roots, isn't it? Sure, so maybe I would check with the graph. Let me try to visualize this. So let me say, yes, a sine x over x will be the product of the plus minus integer pi. So we can actually put it as a product of a quadratic factor, which is going to be made out of the plus minus integer pi. Easy peasy, lemon squeezy. Okay, so let's have a look. So, so if this behavior is truly the same as the polynomial function here, if it's the same, right? If it's the same, the ratio as n gets bigger, the number of terms gets bigger, the ratio should converge to 1. Do you agree with that? Right? For example, x squared plus 1 over x squared minus 2x plus 1. Obviously, their behavior at the small values of x will be very different, but for the large value of x, it will eventually be the same. So the asymptotic behavior will be therefore very, very similar. You see? So now that's what I claim. So I say that my polynomial here, because I know the roots must be that, so I want to see, okay? So then why don't we put this on the graph and truly see if it's going to match, okay? Then you instantly realize that it's going to fail, right? So that's the sine x over x. We saw that with a nice animation at the very beginning. But now if I show you this polynomial, let's say with 10 many terms, with the 10 product, becomes huge, right? And therefore, if you see the asymptotic behavior, let's put the sine x over x as on the top, and then this polynomial with the degree 10 in the bottom, it becomes almost 0 instantly, right? Their behavior, their ratio, the asymptotic behavior is going to be 0. So it ain't the same, right? In order for me to claim that it's going to be the same, their asymptotic behavior must be the same, hence becoming 1. Right? It became 0. So obviously the denominator is a lot faster, which we can easily see from the graph. Okay, what went south? Well, the sine x over x, and then this product of function. And the one thing that I know it's going to fail instantly is about what do you think it's going to fail, right? That will be the proving phase. You learn that this doesn't work. However, we still have a fair point. We have x-intercept, right? If you have an x-intercept, that I should be able to factorize it. But what went wrong? Well, the first thing that I want you to consider is maybe obvious values in the polynomial. What are the obvious values that you can find other than x-intercept? Because we already know it. Very good. The y-intercept. We already know the y-intercept of that being what? 1, right? That was a limit, right? That's the fundamental limit of trigonometry. So if I want it to be continuous at x equal to 0, I'm going to define this function to be 0 here, right? It was indeterminate, but I'm going to claim anyways, okay? But if you look at his y-intercept, you clearly see that it's going to be obviously not 1, right? Because we have product, my friend, product of constant term as n gets large is going to get infinity very, very quick, one way or the other, because it's alternating, you see? So we had something wrong with actually the constant term. So in fact, even if you multiply many, many terms, you want to guarantee your constant term will actually become 1, so that it's going to match with my sine x over x, right? So that is the proving phase, you see? You need to give your thought into the analysis of a function and then think which part of a function may not match in this particular case. And as you can see, it doesn't delve into like advanced calculus or advanced vector analysis, whatever, right? It's really just something that we already have learned. And even though, therefore, even if this question may appear to be very challenging for you, it's something that's definitely doable because you get the commentary from the question. Learning phase and proving phase. And proving phase will require your more deductive skills and answer. Okay, so how can we actually get rid of that constant part? Well, maybe we can factorize it, you see? If I try to factorize everything by 1 over n pi squared, then what you can do is that, if you multiply that, as you can see, what's going to happen here, my friend? You're absolutely right. If I distribute that, my constant term, it actually becomes 1. So no matter how many terms here we have, my friend, it is simply just going to become 1. You see? That's great. That's marvelous, right? Because if you think about it, no matter how many terms, I guarantee my y-intercept to be 1, you see? And let's see if this really makes it better by the graph, which you can use the paper 3 on the calculator, right? So if I give you 10 many terms with that constant term 1 over n pi squared, which is going to reduce my size of it, very close to the sine x over x, and as you can see, it's very close. It's very close. The red one The green one is the sine x over x, and the red one is the polynomial. And as you can see, as x gets a very small value, it's identical. But as you can see, the x gets bigger, then it's going to get bigger eventually because you didn't have enough many terms, you see? So I'm sure if you put 100 or 200, it's going to get better, right? Let me give you 11 many terms, however. As you know, it was an alternating series, wasn't it? Because it was a x squared minus n pi. And then depending on the number of terms, if you multiply even number, you know it's going to be positive. If it's multiplying odd number, it's going to be negative. Like that, right? Like that. Okay, so that's something to consider too. So here we have now this 1 over n pi squared coefficient, which is a very huge reducing factor inspired by my constant term. Okay, that's great. But as you can see, well, it doesn't matter because it's alternating, right? It's alternating. Doesn't matter which way we put. Okay, it doesn't matter which way we put. So now I claim my sine function is going to be the same as that, you see? So I claim my sine x over x will eventually be the same as this. Of course, you got to prove it, right? Once you start working with the analytic calculus, you cannot say things unless you can prove it. But that's a tertiary level of education. In your paper 3, they are going to say, yes, hence what you have derived in the polynomial is actually correct, okay? That's the learning phase. And then what the question will elaborate for you is working with the proving phase, okay? So now, what you can do is to compare the sine x over x in another form. Now we compare this as a factorized form, but okay, it's something to do with the polynomial, right? Sine x over x I'm trying to describe as a polynomial, but we do know the polynomial expression of a sine x over x, which is from the Maclaurin series, okay? So now this is the Maclaurin series over sine x. Now I merely divide by the x. Then I get the even terms, which then makes sense for me, at least that is an even function, right? And I'm going to maybe compare this one, the one that I've derived from the Maclaurin series, the one from the polynomial factorization from my learning phase to work with the proving phase, okay? So now I claim that this, whatever the sine x over x, which we know the Maclaurin series version exists, right? Unless x is equal to 0. And then I now newly came up with the, the factorized form of the Maclaurin series. That's great. And now what the question says, they want to ask you to work with the, the coefficient of x squared. Okay, why not? Let's try. So now I got the coefficient of the x squared on the left-hand side. What is it? Negative 1 over 6x squared. Okay, that's great. Let's try to work with the right-hand side. Okay, if you work with the right-hand side, okay, but let's try to list them out. So it's going to be product of a linear factor of the following. It's going to be 1 minus x over pi boom, 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 square, isn't it? Yes, 1 minus x over pi, what is it? Sorry, 2 pi, a square, and then 1 minus x over 3 pi squared, goes on and on and on, isn't it? Okay, no problem. But as you can see, if you expand them, the least degree will be 0 with the constant, okay? My question to you is it possible to get a linear term? And the answer is no, right? So, and I don't think it's possible to get the linear term here because, because I put the square inside, right? So that it's not a perfect square of it. It's not binomial, but it's a square of that. So as you can see, the least term is a quadratic. And to attain the quadratic, this has to be multiplied only for the constant, which is in this case 1. So if you list only the quadratic term of this, only the ones of that are multiple of 1, you see? So if you list the ones out, it's going to be then, that's negative coefficient. So it's going to be negative 1 over pi square x squared. Negative for that one is going to be 1 over 4 pi square x squared. And for that one, it's going to be negative 1 over 9 pi square x squared. Goes on and on and on. And I will, because of the polynomial equality, term by term, I claim that they may be the same. And here, now x was non-zero value, so I'm going to factorize by the x squared. Okay? And then I'll multiply by the, negative. Okay? And then lastly, I'll put the pi square on the left-hand side. Let's try to multiply the pi square on the left and right-hand side. Then you get the pi square over 6 becoming 1 over 1 square plus, 1 over 4 square plus a 1 over 9 square. Oh, my bad. No, 4 is a 2 square, right? My bad. 2 square, 3 square goes on and on and on. So that is precisely the Basel problem, right? And that is wonderful. Right? That's another proof with the Basel problem, which Euler proved it. But more importantly, what was way more important for you is actually to come up with a factorization method for the polynomial, because you know the roots, but you cannot say it for free because the constant term didn't match and it diverged rather quickly. But what you could do here is to see the reducing factors such as 1 over n pi perfect square in the coefficient, so that the constant term is going to actually become 1 no matter when. No matter what many terms, right? But we didn't prove it. However, though, the asymptotic behavior is 1. What you could have done is to see the ratio between the sine x of x and this polynomial that you came up with, that we got it from the question, and send the n to infinity and see if it eventually becomes 1. Right? That's what we had to show it. But that's another paper 3 question maybe. But I wanted to show you that yes, what you have proven can be used for deriving the solution. Okay. Okay. Let's have a look at the. It's a Basel problem number 4. Okay, it's a number 4. We're using the reduction formula. Okay, so for this one, it's quite challenging. Okay, it is challenging because your work is very tedious, meaning it's very lengthy. But we are not going to use anything fancy, okay, other than integration by parts. That's all I gotta do. So it's not that bad. However, mathematically, this is very rigorous in terms of algebra. So I really want you to fasten your seatbelt and follow. Okay, let's take a quick pause and then come back. Thank you. Okay, let's have a look at the last problem for the Basel problem, okay? Using the reduction formula. So what is a reduction formula? It's just a repetitive integration by parts, but for the integration by parts, it depends which one you want to use the antiderivative, right? So what I mean by that is, for example, what you can do here is x times e to the power of x, and imagine that I want to do this by parts. And for me, it's very obvious which one you're going to keep differentiating to reduce it, and keep integrating to change the form. And we do know that we're going to differentiate that, right? But for example, if I have a cosine to the power of n, and then you want to do this by parts, what you can do is many different versions of integration by parts, right? For example, maybe you can do cosine and degree 1 dx, and then keep integrating this and then keep differentiating that, okay? Or you could have done, cosine n minus 1 x and cosine x, and maybe keep differentiating this, maybe keep differentiating this and keep integrating that. So there are many different versions of it, right? So that's my point here, okay? And this problem really tackles on which, depending on the order of integration by parts, which one you are going to arbitrarily choose to keep differentiating or integrating, changes the form, and you can associate with the values, okay? So let's have a look what I mean by that. Right now, in this problem of the learning phase, it's going to take a while with the learning phase. Please fasten your seatbelt. An is given as the, cosine integral of degree 2n. And then bn is the same kind, but now I got the x squared. Okay, remember, an doesn't have x squared, bn has x squared. That's all you got to remember. Okay, so let's go. So now what we want to show here is to show by the integration by parts that this an will have this following recursive form. Remember, for the reduction formula, often it's not going to stop once or twice to integrate and have a final form. Reduction formula insinuates that you're going to do this n many times, and for that, what you want to derive is essentially a recursive form. Okay, so integration by parts advanced form is a reduction formula, and that reduction formula is often associated with the recurrence rate. And of course, our job is to change it to explicit. And so let's have a look what we can do. Okay. So right now we had the an was the without the x squared, so I'm gonna do the integration by parts of that one. Okay, so now it's a learning phase, so let's see what learning phase we can do. Okay, so we got the following example. Then I'm going to break down into product of the cosine degree 2n minus 1 and then the cosine x. Okay, and what I'm going to do is now I'm going to differentiate that, and I'm going to integrate that, right? Because this cosine x is a lot easier to integrate than what we have is cosine 2n minus 1. Okay, all right, so then this is a definite integration by parts, so please make sure, so we leave it, integrate, so we got the leave it, integrate, we got the cosine, very good. And then differentiate, integrate. So we got the sign here, but now you got to differentiate this. But for that, you got to use a chain rule, don't you? So 2n minus 1 times cosine to the power of 2n minus 1 times negative sine x will come out by using the chain rule. By the way, when we do the definite integration by parts, we got to evaluate for the first product here, 0 to the power of 2. Well, 0 makes the sign 0, doesn't it? And then the cosine at the power of 2 will become 0. So at those two values, I'm going to have a 0 there. Easy peasy. lemon squeezy. Okay, so we got this value here. So now let's try to simplify the integral. So I take out the coefficient 2n minus 1, and I try to leave it like that, right? And then I got the, what is it? Sine and sine, right? I got twice product of a sine and sine, so it's going to be sine squared. But remember, my given sequence an and bn had a bunch of, what is it? Only the cosine, right? So it's probably worthwhile for us to only convert into the cosine form. So here, from the sine square, I can use a Pythagorean identity and then apply it accordingly. So if you do the distribution, what do you get? It's going to be, what is it? Cosine 2n minus 1, and then 2n minus 1 times cosine 2n, right? Because if you do the distribution here, well, that's precisely what is it? That one is going to be an minus 1, isn't it? Because an is defined for the 2n, an minus 1 is going to be integral from 0 to pi over 2 cosine twice of the n minus 1. Please mind the multiple. So therefore, when I see the 2n minus 2, that can be converted into the an minus 1, whereas for that one will be simply just an, no problem, right? So let's try to write this one down. So now for that one, so now if you, what I've just done now for you is rearranged, right? So that is to associate with, this integral is to associate, what is it? An, that's an minus 1, okay? So if I then simplify it, what you can do here is to realize that we can have a look at this following recursive form as expected, okay? Sure, so we did the integration by parts on an, where we had the power of 2n, but we did the 2n minus 1 times cosine and then do the by parts and use the Pythagorean identity to bring it back so that we have desired sequence, okay? But then the question says, now I got the a and bn, sure, but now for the second part, I want you to do by parts again on an, but differently, so that you can show this following form, okay? But look, now my an is no longer in the recursive form, but another integral. But you know, once you got the result, and then it's still in the process of the learning phase, you really should sort of consider how to use the given result, you see? Because often the answer or the critical approach to get to the answer relies on the result that you are proving it, right? So what I mean by that is, now I got this x integral here, sorry, x within the integral, whereas for my an, I didn't have it. So how can I somewhat come up with the x when I don't have the x in my expression? Well, for that, we're going to take another approach of integral by parts. Now, this time, as we maybe as discussed before, we could probably go from 0 to pi over 2 cosine 2nx times 1. And maybe I will keep integrating on 1 so that I can have somewhat expression of the x. That's how you choose it, you see? As I've said before, there are many different variations of this integral. Maybe you could have done it as a 2n minus 2 times cosine square. Who knows? But however, in the desired answer form, I have the x. So I need to somewhat come up with the x, and instead of dealing with maybe cosine square, dealing with 1 is a lot better, because if you integrate, my friend, I simply just get x. So that's correct. So sure, now I'm going to approach, what is it, integral as the following. It's going to be 0 to pi over 2, and what is it, cosine 2nx times 1. Right? So as you can see, that's the one I'm going to integrate, right? So that's why I have x times cosine 2x, and then differentiate then an x. So I got the x, and then the derivative, we already found it before, right? So that's what we have. And if you put 0 and pi over 2, as we have done before, that would simply be 0, no problem, okay? So then here, who's going to come out? The independent term 2n is going to come out, right? It's a double negative here, so it becomes a positive. I got that. So now I got the product of x, cosine 2n minus 1, and then the sine x as desired, okay? That's great, and that's what we have, right? So that's another expression for the an. So now we have expression for an in a recursive form as well as an integral. So that's great. Now it says use the parts on the integral on the part B to show another recursive form, right? For the second part where we did the an with the cosine to the power of 2nx times 1, right? And then it's asking me to use that to get into the recursive form, right? Okay, so let's have a look. How can we do that? So we got this integral form first. What we're going to do now is to perform another integration by parts, because like I said before, integration by reduction formula may not stop at 1 or twice. You might actually have to do repetitively to find the pattern. So in this case, from the previous part, we had an x here, right? But x is the derivative of the x squared over 2, so that I can keep integrating this for what is it? for finding the the integration by parts, right? We had an x before, but I put it in the derivative form like that so that you can see more easily which one you have to integrate, okay? So that's great. So now let's perform integration by parts once again. So this part we got it by once. Now I'm gonna do it twice, okay? So I'm going to differentiate that and integrate that. It's gonna be a hell of a journey to differentiate that because I gotta do what is all this product rule and chain rule, which is not that bad. Oh. Maybe not. Maybe. Oh yeah, we have to, right? So we leave it, integral, I got that. So I go integral from 0 to pi over 2, no problem. Now you got to differentiate this, my friend. Like I said before in the beginning of the video of this question, I said this is not a challenging problem because it doesn't use that much of advanced mathematics, but algebraically it's very tedious, and so for which you still have to do it. Okay, it's part of the job for the paper 3 and AA, but it's definitely a doable job because it's a product of function. So I would suggest that you do the product rule and chain rule. Okay, and then you still have to integrate that one. So I got the x squared over 2, no problem. So I got this following integral like this. Very nasty, very nasty. Well, for the evaluation from 0 to pi over 2 for this one, again, if I put 0, that's a 0. If I put pi over 2 on the cosine, that's a 0. Easy peasy, lemon squeezy. So now I'm looking at the second integral here. Okay, maybe I would like to see which one I can simplify more first, maybe, right? Maybe I put the cosine x here and then the sine x there. And furthermore, my friend, I got the sine square. Maybe you can derive the Pythagorean identity once again, right? Let's see. So I combined them to combine this. I got the cosine twin. I got the sine square here, my friend, for which we already talked about before, right? But maybe you can use the Pythagorean identity. Why? Because my sequence AN or BN, they were all listed in terms of a cosine power. So maybe I don't want to have a sine power. That's the whole logic behind it by using the Pythagorean identity. All right, so then, yeah, you still have to do the algebra a bit, doesn't it? Because you got to distribute this and then combine this again. You know, it's a bit of a job, but it's a bit of work, but you know, you can definitely manage because it's simply just algebra. You got to get your hands dirty, okay? All right, that's great. So then remember, so now I did the expression and then expansion and trying to factorize with the like terms. I got into the following, right? Then please remember the AN was from 0 to pi over 2. What was it? Cosine power 2 and x dx, okay? And the BN is the same kind, but on the in the integral, what was also multiple? It was multiplied by the x squared, isn't it? Sure. So I would do x squared like that. Okay, so that's the integral that we have. That's AN and BN. I love it. Okay, so then that one, obviously, do you think it's going to associate with the AN or BN? Very good. It's going to muy bien. It's going to associate with the BN. Why? Because I got the x squared on my product of the on the cosine, and here it's going to definitely associate with the AN because it doesn't have x squared. Right. So let's see how we can simplify. So yes, that is going to be BN minus 1. Oh, my bad. Oh, sorry, this is a bracket here. You got to multiply all this actually. Never mind, sorry. Everything is going to be in terms of Bn, where that's going to be Bn minus 1, and this is going to be simply just the Bn, okay? So that's great. So that is the expression of the An in recursive form in correlation with the Bn, okay? Easy peasy, lemon squeezy. So this integral, this algebra is not that challenging. It's just lengthy. And you cannot give up just because you got a chain rule of a product of a two-trig function. Okay? All right, so I got it. You know, we got the recursive form, no problem. That's great. So then it's still learning phase. It says, okay, we already had the first learning, the expression of the AN in the recursive form when we perform the integral of what is it? Cosine to the power of 2nx as a cosine to the power of 2n minus 1 times cosine x. I'm going to compare that recursive form into the one that we just derived on the part C. Okay, one way or the other, they are the same, doesn't it? Okay, so I'm trying to intend to show this. Okay, let's try to show that one. So this, my friend, is from the part C. Okay, this was part C, and now what we were going to do is to rearrange this to the left-hand side, to the right-hand side, sorry, by dividing it. And in fact, we saw the expression of n times an. That was precisely from the part A. That was the first recursive form on the an using the product of a cosine 2n minus 1 and cosine, right? That is great. So I just quickly used it, right? Remember, we're still doing the an right now. Sorry, we're not doing an. We're doing 1 over n squared. That is great. This is from part A. That is lovely. That is wonderful. And then what we can do is, of course, we can put it into the common denominator, sorry, not common denominator, but try to simplify further by making the common factor here cancel out. So 2n will be just put on top, right? And then the n cancels out here too, so only 2 comes out, no problem. What comes down goes up. So now that's great. So that's the expression we have. Now we factorize it by 2, and that's the result that we wanted to show. We simply have, what is it? Sorry. Now we simply have 1 over n squared being the following. So that is great, that is wonderful. Sure, so now we want to show this identity derived from the previous part. Again, remember, this is going to be now, let's say, proving phase, and because it doesn't ask you to use which part, right? Previously, of the sub-questions, you saw use this and show this from this part. That would be considered learning phase because it gives you the steps to use. But for this one, we consider proving phase because it doesn't give me the steps to use, right? We have to think about it. So proving phase is the ones that is missing the hints, okay? So let's have a look. So now we had, what is it? 1 over n squared, wasn't it? And then we are trying to associate, the question asked me what? Let me go to the previous slide. The previous slide is trying to find the sigma form of 1 over k squared, where we derive something from the 1 over n squared. So why don't we change the terms here in terms of k? And put what? Very good. Let's try to put a sigma on both sides with the index of k, for which I just did it for you, right? Then this expression will be given as the following. But really, from your, the algebra practice, I hope you realize this really reminds you of something called a telescopic cancellation. It reminds me of a telescopic cancellation. So what does it mean? So the ones, telescopic cancellation, after the expansion of a sigma, you will see a lot of a cancellation, and then whatever the term is left, it must be symmetric, okay? Sure, so what do we see? Well, if you group by the 2, then this and this is a like term, that and that is a like term. So all the terms will be left over other than the first, and it has to be symmetric, my friend, therefore the last term. So we got that, okay? So that is it, right? So now the Basel problem here will have the form of, what is it, of the following expression. But what we still have to evaluate is probably this value here, for which we can just put the n equal to 0 in this case, and let's try to evaluate the integral, no problem, right? Because bn, my friend, was the integral from 0 to pi over 2 x squared cosine 2nx. Of the x, and the an was what? Oops, sorry. An was 1 without the x squared. And now if I put n equal to 0, voila, that's not that bad because that's a quadratic constant for which we can easily perform the integral. Piece of cake. So I've got it for you. So I got the pi squared over 6 for the first term here. After the telescopic cancellation, an integral for the initial term n equal to 0. Easy peasy, lemon squeezy. Okay, so then I have this following expression of the Basel problem for the finite sum being pi squared over 6 minus 2 times bn over an. Okay, then obviously the question insinuates now I want to know what happens if I set n to infinity. Then I want to show the asymptotic behavior of the bn over an will eventually become 0. Okay, sure. So let's have a look. So now again, this is a learning phase, so you can use it for free, no problem. Do not try to derive it. You can use it for free. Well, of course, you can show it by using calculus. So now I want to show this identity. I want to show that the bn is bounded by this following integral. Okay, using that, I got to use this. Okay, how would you like to use it? Where we know already the bn was integral 0 to pi over 2 x squared times cosine 2nx, right? So that was it. Okay, but I got to use that identity. At the moment, from the inequality that we are given, I got nothing to do with the cosine, right? Because I need to have some expression of a cosine. And yes, very good. So for that, I like to use actually maybe the Pythagorean identity because I got to change into cosine squared first and then put into the power of n. That could be the first step, isn't it? Okay, so let's see what we can do with this inequality. So we were given this inequality, right? And then what we can do is we squared it. And please understand, you know what? Being able to have that inequality is not important. That importance is probably 1 out of 10. The 9 relies on the fact that you wanted to square it because so that you can link something with the cosine square. That's mathematics. That's called deductive thinking. It doesn't matter if you can evaluate this after this. After that, it's just boring work. okay, of making things look pretty. This is the dirty work. Why am I squaring it from the given inequality is a super more important, especially it's going to be more complicated either in paper 3 or competitive math, okay? But anyways, we did that. Why? Because we wanted to derive something with the cosine. Why do we want to derive something with the cosine? Because I have to somehow eventually associate with the, cosine, Bn, which contains the x squared and the cosine to the power of 2. And I didn't have any cosine, so I squared it so that I can use the Pythagorean identity, okay? That is great. So now using the Pythagorean identity, I've got this, okay? So then let's rearrange a bit. So now I rearranged beautifully for making the cosine square as a subject. So I've got this, right? Oops. So this is separate, okay? So I've got that. And then for induce to Bn, what you want to do is maybe to put it to the power of n, isn't it? So I put it to the power of n. On the right-hand side, I got the power of n as well. No problem. But for the Bn, I got to have eventually who also? Yes, the x squared. So I'm going to multiply by the x squared. Oops, sorry. So in this part, in this inequality is a separate. So I just put it into the power of n, right? And then we multiply by the x squared and then integrate from 0 to power of 2, right? Then you will see, that on the left-hand side is same as the Bn, but on the right-hand side, that multiplied by the x squared, integral from 0 to power of 2, will be your upper bound. Wow, fancy inequality started from something very small. Okay? No problem. Easy peasy. Lemon squeeze. You got an upper bound for the Bn. Okay, that is great. Now, I want to show that integral, the upper bound, is actually the same as that one. Okay? And then I want to use that derivation into the fact that now the Bn can be bounded by the following, right? Which is obvious because this was his upper bound, so then it's just different version of the upper bound, isn't it? So let's show whether you can do the part G. And then later on, we're going to use the substitution to show that Bn can be actually upper bounded further by the following expression in terms of An. Oh wow, what are we talking? Don't worry, we're going to get into it, okay? Let's try to simplify the terms. So now what I've done here, look, I will show you. What I've done here now is actually, it's even more, it's a harder deductive thinking to my understanding, is that I have to show this. This is my aim, isn't it? This is my aim. To show this, what I would ask you to do is to start maybe on the right-hand side. You could have started on the left-hand side, but for me, every time you want to prove something, it's easier to start at the nasty part. If you start with the nasty part, there's more room to simplify. And for that case, you can go into the you can then go into the simpler form. If you start from something clean, it's really difficult to choose which dirty parts you want to add or subtract or multiply. Okay, so proving, you always start with the nasty part. Okay, so I started with the nasty part here. So that's what I've got. Okay, so from here, what I would perform, okay, what I would perform of this integral using the, integration by parts again, right? So I wanted to integrate this by parts, but here I got the 1 there, don't I? So for that one, I keep differentiating this one, I integrate this one. So the initial form of that, multiple of the x here. So that's what I've got here. I got the bound from 0 to power of 2. You can easily plug it in, but if you put 0, that will be 0. If you put power of 2, my friend, I get, 4 over pi squared times pi squared over 4. This cancels out, becomes 1. 1 minus 1 becoming 0. So this will become actually 0. No problem, okay? So here, then, it's going to get a bit nasty, doesn't it? Because I integrate that one, so I got the x, right? And then you got to differentiate this factor because that's what we decided with. So if you keep differentiating using the chain rule, we got this form. No problem. We're going to simplify, okay? Beautifully, this value here was a 0. I'm very happy, okay? Now I'm left with what? Oh, this one. But now, thankfully, what you can do is I am left with that, okay, first of all, right? And then the x, and then the x got multiple. I got the x squared, right? So, and then I got the pi square. I got the pi square. I got the negative pi. I got negative 8. I got negative 8. Canceled out. Beautiful. N plus 1 canceled out. So I just only have that term left alone in this integral with the x squared. Okay? Great. Okay, great. So this is the form that we have, which was precisely. So now it's equal. It is not a bound. This is an equal version of it, which is the upper bound that we found. Okay. So then, Bn was bounded by, the previous integral from 0 to power of 2. It was that one, right? X squared, boom, boom, whatever to the power of n. But now we show that this actually is the same as that one. Okay. So hence it must be the upper bound also for the Bn. no problem. But this question didn't stop there. Now I have to somewhat associate this upper bound with the multiple of, some factor multiple of the an. Let's see what we can do, where an didn't have any x squared on the integral, right? So now they gave me the substitution. Why don't we use it? Every time you're given the substitution, there are three things you got to do. Substitution, you differentiate and make the derivative not with respect to x, but the one with you are substituting with. So now my substitution contains with t, so I have to associate with the dt. Okay, so you differentiate the x with respect to t, and then move the dt on the right hand side, and that is the one that I'm going to substitute for my integral with the dx. Okay, so that's great. So when x equal to 0 and t equal to 0, what we have here is x equal to power of 2 and t is equal to power of 2. Make sure this is what changing the definite integration by substitution. You cannot leave the bounds the same. They change accordingly as well because of the substitution. Okay. And also, I want to remind you for that form here, 1 minus 4x squared over pi squared, where the x now was a sine pi over 2 sine t. If you plug it in, that cancels out. So I'm just left with 1 minus sine squared t, which becomes a cosine squared t. It's easy lemon squeeze. So actually, we can come up with the Pythagorean identity to plug it in here, right? And then, so this is before we move into the next slide, let me quickly show you then what we're going to do. For that integral, how therefore, it's going to be for the zero value, t was a 0. For x equal to pi over 2, t is going to be pi over 2. Okay, that's beautiful. The bounds remain the same. And then the first one in the bracket, that's going to be cosine square t to the power of n plus 1. However, we are not done because you also have to replace the dx, my friend. Please, this is integration by substitution. So dx is given as what, my friend? Pi over 2 times cosine t dt is what we have. You see? So if I put them all together, that's going to be pi over 2 from 0 to pi over 2. And then what is it? Cosine square t to the power of, what is it? N plus 1 times cosine t. Where that can be put it back into what? 2n plus 2, isn't it? Because there's a power to the power, so it simply becomes the product. Okay? So that is going to be the one that we have at the moment, right? So let me unfold this. So that is what we have here. Okay, that's what we have. Well, with the same multiple, I can raise the power by 2n plus 3. Easy peasy, lemon squeezy. Okay, so now let's try to isolate by the an and cosine cubic. Why? Do you know why we are doing this? You know why we are doing this? Because I want to somewhat associate with the an. We already had the answer. For the paper 3, for the proving phase, there are many different ways to, there are many different ways to branch this out. But now I have to somewhat make the connection from my dot, for present dot, to the dot that we were given to show. Right? We had to show the upper bound was somewhat to associate with the an, and the an was just in terms of what? 2n. It had nothing to do with the cosine cubic, and it had to do actually with the inequality. And as you can see, cosine cubic t, the range is going to be between 0 and 1, isn't it? So now I know this will be obviously arbitrarily smaller than pi cubic over 16 n plus 1 from 0 to pi over 2 cosine 2n t dt. Oops, sorry. Right, because this is any multiple that is between 0 and 1 would make things smaller, right? So that is great. So now we can gain this upper bound because of thanks to the range that we already know for the cosine. Makes things smaller always. The best part is, at most part would be when it's a 1, right? And then that's great. And please make sure this, just because I have a different variable, this evaluation doesn't change anything. It's because it's called a dummy variable, isn't it? Remember, from 0 to 1, x squared dx will be identical as from 0 to 1, t squared dt. It's called dummy variable. It's just a variable that we use for evaluating the integral. So that is precisely, therefore, the definition of an. Just because I don't have the expression of dx doesn't make it non-an, okay? So that is great. So here, the upper bound here is going to be therefore something with the an. So now we just came up with the fact the fact that the bn, okay, was less than or equal to pi cubic over 16 n plus 1 an. Oh wow, voila, that is great. And what are we going to do? We're going to rearrange this an on the bottom here. And then let's send n to infinity and beyond. And then you see the upper bound is actually going to become 0. Well, those were the positive term because it was something to do with the perfect square. Remember, bn was x squared and the cosine 2n as it's a perfect square, so it's integral from 0 to whatever pi over 2, it's going to be positive. AN was the same thing, same sense, so it's positive. All right, so by the squeeze theorem, that sequence actually will go to 0. So that is beautiful. That is beautiful. So we got this part here, and so yeah, that was upper bound of the Bn, isn't it? Okay, that's great. So yes, it's just a rearrangement here. We already established that becomes a 0, so no problem from the squeeze theorem. It's okay, right? And then so what you realize that your series will be just left alone with the pi square over 6. Okay, by the Sandwich theorem, yes, that limit here will become 0, and that is bounded by pi square over 6. So the whatever one between by the Basel problem will converge to pi square over 6. Okay. So I hope you really realize this here. I'm not doing any fancy integral here. I'm not using any hyperbolic function here. I'm not using any double integral. I'm not using partial derivative. I'm not using any double integral here. And I'm not doing change of variables here, okay? I'm not using any fancy differential equation. I'm not using integrating factor. I'm not using auxiliary equation. I'm not using Bernoulli differential equation. I'm not using Riccati differential equation. I'm not doing any of that. It's all within the things we already have learned. It's just algebraically very lengthy. But what you really have to emphasize here is that why am I squaring the sign? For example, my inequality. Why am I trying to make things even? Why is it okay for me to say the cosine cubic is bounded by 1? Hence, I can come up with the upper bound. Why do I want the 1 instead of a cosine cubic? Well, because we wanted to associate with the AN. All those things is considered what? The deductive thinking. And that is the essence of the proving phase, my friend. Okay? All right, so that's pretty much it for me today. For me today, I wanted to show you just what you have to focus, okay? The first thing is that, yes, you can gain some insight of hard problem that you might have not seen before, such as, sin x over x, or alternating thing series, or like once we saw gamma function from the past paper, or the hyperbolic function. You can sketch the conic section and the graph entry on the Inspire, things like that. If you struggle with something completely new, try to play around with especially the graph on the calculator to gain the insight. It might help you. But most importantly, for the paper 3, there are 2 steps that you must acquire. At least you should be aware. What is it? Learning phase and proving phase. And learning phase will probably be governed by the things you already know of, you see. But proving phase is more of the new things. However, you really have to associate with the things you know, right? It's not about the fancy calculation you can do. It's about the step you can make, right? You're given this information. Can you use it? You're given this result. You are not given any hints, but can you make the jump, right? Can you make that jump is the essence of a paper, okay? But yeah, that I conclude this video. That's pretty much it for me today. See you. Good luck for the test. Sorry, exam.